Homework solution 2.4. Determine the total current or voltage supplied by the sources for the following figures. We've got two figures here, one with parallel resistor and inductor, and then one with a series resistor and series capacitor. So those are our givens, or these diagrams. What we're asked to do is determine what the total current is here and what the total voltage is here for those circuits. Find those. The solution method. So in solving this problem, we're going to say that the voltage is the reference, and then that's going to allow us to determine the voltage across the resistor and the voltage across the inductor. We can then use Eli the Iceman to determine the relationships. We'll do the same thing for this. So if we let Vs is equal to the magnitude of Vs, it's just got some size, 5 volts, 10 volts, doesn't matter, at an angle of 0 degrees. So we've taken the voltage source as the reference. We know that voltage and current are in phase in a resistor. The voltage from here to here is magnitude of Vs at angle 0. That means the phase of this current vector has to be the same as the voltage vector. And so we get I in the resistor is going to be 8 amps at an angle of 0 degrees. That makes it in phase with the voltage. And then we know that current and voltage are 90 degrees out of phase in an inductor, and current lags the voltage in inductor. So IL, we've got 14 amps as the magnitude given to us in the figure. And since the current is lagging the voltage, we know that it's got to be at negative 90 degrees. So what that looks like in a phasor diagram is that we've got a resistor current 8 at angle 0. We've got an inductor current at 14 at angle negative 90. And so the total current by Kirchhoff's current law, because the sum at the currents at that node has to equal 0, this current coming out of this source here has to be equal to that vector plus that vector. So the magnitude of the source current is going to be equal to the square root of 8 squared plus 14 squared. And that's going to give us 16.12 amps. And the angle that the current is at is going to be equal to the inverse tangent of 14 over 8, and we need to make sure that that angle is in the fourth quadrant. So we get inverse tan of 14 over 8. That gives us 60.26, and to put it in the fourth quadrant, we just put a negative sign in front of that, negative 60.26 degrees. And so we combine those together, and we find that the total current sourced by that source right there is going to be 16.12 at an angle of negative 60.26 amps. So that was a demonstration of KCL there. For this other circuit here, we are going to use KVL. And overall, we know that this circuit has a capacitive nature to it, and therefore the current flowing through this is going to be in the first quadrant. Remember that the impedance diagram for this circuit is going to look something like this. We've got an R, we've got an X that's reactive, it's capacitive reactance, so it goes negative. So this is Z here. And what we have said many times is that the current is going to be opposite, the angle of the current is going to be opposite the angle of the impedance vector, which means the current is going to be, if this is the complex plane, the current is going to be somewhere up in that first quadrant. We don't know exactly how much because we don't know the angles of these, but we know that that is going to be the total current, something like that. So that's what we're going to use to solve this problem, is that the voltage through the resistor has to be in phase with the current through it. So we know that the voltage through the resistor and the current vector, they overlap one another, at least in angle they do. We'll take the source as the reference, so that's going to be Vs, and then we know that the capacitor current and voltage are 90 degrees out of phase, and from ice we know that the voltage lags the current. So I've got my capacitor current right here. I needed a voltage across that capacitor that lags this current by 90 degrees. That's going to be right here, right? That's a little 90 degree mark right there, and that's going to be the voltage across the capacitor. So the current through the resistor and the voltage across the resistor are in phase. The current through the capacitor and the voltage across the capacitor are 90 degrees out of phase, with the current leading the voltage. Ice. I didn't write it, but that's Vs. So that's the phasor diagram for that. We're going to change it a little bit. We're going to use vector notation. We're going to say, okay, we've got Vs is our reference there, and we've got two other vectors. We're using I think you can see we're using the tail to tip method of vector addition. This is V sub c, and this is V sub r right there. And so you can see what we've established is that we've got a right triangle for this circuit right here with three elements in it. And if we were to write this phasor diagram, having a little trouble scrolling today, sorry about this. If we were to write this phasor diagram as a math equation, we would say V sub c at 90, let me slow down there. I think I'm jumping the gun. I'm having all sorts of troubles with this. Nothing's erasing. I'll just scratch this out for now. I don't know why things aren't erasing. In this example, we had used phi as the angle. Phi would be this angle right here. It's the angle between the voltage and the reference phasor. And so that's actually this angle right here is phi, which means this angle's phi, which means this angle's 90 minus phi. So that's the angle of the voltage across the capacitor. V sub c at an angle of 90 minus phi. And then it's V sub r at an angle of phi, right? V sub r's got an angle of phi associated with it, and that's going to be equal to Vs at angle 0 degrees. So that's the phasor equation. I could use Pythagorean's theorem, and I could just say the magnitude of V sub c squared plus the magnitude of V sub r squared is equal to the magnitude of Vs squared. So we know that V sub c was given to us in the problem statement as 3.2 volts. V sub r was 1.8 volts. And we know that that's equal to the magnitude of Vs squared. And that gives us a value of Vs is equal to 3.67 volts. And so since it's the reference, we'll just say that's at angle 0. So we could, that determines the total voltage across the circuit there.